Although VAEs and GANs are the most popular kinds of deep generative models, there have been other methods that have also been successful over the last few years. Let's see a few of them in the last lecture for this week. These models are generally known broadly as flow-based models. How do they differ from GANs and VAEs? There's a very important difference between them and GANs and VAEs. Both GANs and VAEs do not explicitly learn the probability density function of the real data. In case of GANs, we already saw that the density estimation is implicit. You don't explicitly assign a probability density function and try to estimate it in a GAN. In case of VAEs, we get an approximate density estimation by optimizing your evidence lower bound using variational inference. In both the cases, you don't get the exact density function. However, the exact PDF P of x of your real data may be useful for many tasks such as missing values, sampling data, or even identifying bias in data distributions. Knowing the density function could be handy for these kinds of tasks. So the kind of methods that we will discuss in this lecture are methods that estimate the real density of the provided training data. Broadly speaking, these can be categorized into two different kinds: normalizing flows and autoregressive methods or autoregressive flows. Let's start with normalizing flows. Recall that in the first lecture for this week, we tried to ask this question that if we had a data set of n data points coming from an underlying distribution PD of x, we wanted to find a theta belonging to a family of distributions m in such a way that the distance between p theta and PD is minimized by that choice of parameterization in M. And we also noted at that time that if the distance here was replaced by KL divergence, this turns out to become a maximum likelihood estimation problem, or by minimizing the negative log likelihood. Why is this important? All methods that we covered so far while training neural networks can be looked at as a way of minimizing negative log likelihood. Whether be it training a neural network using mean squared error, or whether training a neural network or an LSTM using cross entropy loss for a classification problem, one can show that both of these finally amount to minimizing the negative log likelihood. So we are now saying that we could use a similar approach even in an unsupervised learning setting. Where do we go from here? So what flow-based models try to do here is, if you could look at GAN as a discriminator and a generator, where the discriminator is the one that distinguishes between real and fake data, and the generator takes you from a latent to a generated image x prime, which is then provided as input to the discriminator along with the real data x. Similarly, VAE is an encoder-decoder model where the encoder captures the approximate posterior q parameterized by parameters phi, which are the weights of the encoder. Similarly, the decoder captures p theta of x given z, which is where theta are the parameters of the decoder. So in this case, it's an approximate density estimation, as we just mentioned. And in flow-based generative models, we do what should have been obvious to do, which is, but not very simple, which is given x, find a function f to get us a latent representation, which if we invert, we get back x prime or the reconstruction. So the challenge here is how do you find these functions f which are exactly invertible to get back your original data. Clearly that's the challenge. So in the first class of methods in normalizing flows, the main goal here is to identify a transformation f which takes you from z to x. If you recall, z is once again the latent, very similar to VAE. The main difference between VAE and flow-based models is in VAE, the encoder captures an approximate posterior with a different parameterization and the decoder captures p theta itself. So we know that q phi is an approximation of the true posterior p theta of z given x, whereas in flow-based models the functions are an exact inverse. So here we identify a transformation f that goes from z to x, where the transformation f is a series of differentiable bijective functions f1 to fk in such a way that x can be written as f of z, which in turn can be written as f sub k composition, f sub k minus 1 composition, so on and so forth until f1 of z. And conversely, z can be written as f inverse of x, which in turn can be written as f inverse composition f2 inverse, so on and so forth till the final composition fk inverse of x. Diagrammatically, given a latent variable z, which could be a Gaussian, very similar to GANs, you pass this vector, input vector that's sampled from z through a neural network f1. At this point we'll just call it a function, which outputs z1, which goes through f2 and so on and so forth till fk, which we finally expect to output the original data distribution that x comes from. Let's see this in more detail before going to the implementation. For any invertible function f from z to x, using change of variables of probability density functions, we can write px of x is p of z, pz of z, into the determinant of dou f inverse of x by dou x. Why? It's not difficult to show it. If z belongs to a distribution pi of z, is a random variable, and x is equal to f of z such that f is invertible, so z would be given as f inverse of x, then from definition of the probability distribution we have integral p of x dx, which would be 1, would also be integral pi of z dz. Both of them would be 1. So from this equality we can say that p of x can be given as pi of z into the gradient of dz by dx, the absolute value. But we already know that z is f inverse of x. So we're going to put that here. We would have pi of f inverse of x into the gradient of f inverse of x by dx, which we are writing it as pi of f inverse of x into f inverse prime x, where prime here stands for the gradient. In vector form, this would be p of x is equal to pi of z into determinant of dz by dx, or pi of f inverse x into determinant df1 df inverse by dx, which is what we wrote here in the first place. If we took the same expression here and if we expanded it and applied log on both sides, we would then get log p of x, which is the log likelihood of the density that we are looking for, px of x, would now become the log likelihood of z plus summation going from I to 1 to k log determinant of dou fi inverse by dou zi. How did this come? This came by substituting f with a composition of functions f1 through f capital K. So that composition, while taking log, becomes a summation. That's how we got this expression here. So the intuition of these two terms in estimating the log likelihood of the probability density function is, the first term here can be looked at as the transformation molds the density p0 of x into px of x. That's what it would like to do. And the second term here quantifies the relative change of volume of a small neighborhood dz around z. Remember, that's what gradient measures. That's what determinant would also measure. Determinant you can look at as capturing the volume of the space that you're trying to measure. Here is an illustration to understand how normalizing flows work. Assuming that you sample from a Gaussian initially, which is z0, you apply a function f1, get z1, then you would apply another function, so on and so forth till you get zi minus 1, zi, and finally you keep applying many functions until you get zk when the probability density function transforms this way, which is the density function of x that we are looking for. Why did we say we want a differentiable bijective function? Why should each of the f's be a differentiable bijective function? It should be fairly straightforward. We already saw how the inverse was being used, but let's define it more formally. Such a bijective function, the way we are using it, is called a diffeomorphism. Diffeomorphic functions are composable, which means given two transformations f1 and f2, the composition is also invertible and differentiable, which is very important when we are working with neural networks. So any complex transformation from a Gaussian to a complex probability density function of the real world data can be modeled by composing multiple instances of simple transformations. So what do we need for normalizing flows? We want the transformation function, each of them, to be differentiable. So that should give us the answer. If each of those functions that take you from z to x is a layer of a neural network or an LSTM or a set of layers of a neural network, they are differentiable and we have met the first prerequisite. The second is that the function must be easily invertible. How do we do this? We'll see in a moment. And the last is the determinant of the Jacobian should be easy to compute. Why? Because that is one of the terms in your loss function and you want that to be easy to compute so that you can train the entire network using gradient descent. Let's see one of the earliest efforts in implementing normalizing flows. This is known as NICE, Nonlinear Independent Components Estimation. This work was published in 2015 by Laurendin et al. The idea here is to introduce what are known as reversible coupling layers. Let's see what those transformations are. So the coupling layer operation used was y1 was the same as x1. So if you add x1, x1, x2 are the different dimensions of the data x. y1, y2, so on and so forth are the different dimensions of what you're trying to generate, which you would like to match x in principle. So y1 is equal to x1. y2 is given by some function g of x2 and m of x1. So you can see here pictorially y2 is given by g, function g, which is applied on x2 as well as m of x1. Note that in this particular formulation y1 does not depend on x2 but y2 depends on x1. In this case it's clear that the Jacobian will be a lower triangular matrix. Why do you say so? Because y1 does not depend on x2. So all these upper triangular elements of the Jacobian matrix would become zeros. Let's take a moment to recall what a Jacobian matrix is. A Jacobian matrix is the matrix of all partial derivatives. So if you had an output vector y which contains y1 to yk, and if you had an input vector x which was x1 to xd, all the pairwise gradients dou y1 by dou x1, dou y2 by dou x1, dou y3 by dou x1, so on and so forth till dou yk by dou x1, and similarly dou y1 by dou x2, dou y1 by dou x3, so on and so forth will form the rows and the columns of the Jacobian matrix. So it's a matrix of first partial derivatives between a vector and a vector. So in this case, you can see that all the upper triangular elements, because of the construction of the operation, y2 would depend on x1, but y1 would not depend on x2, x3 or anything till xd. Similarly, y2 would depend on x1 and x2, but not on x3 to xd, which means all those upper triangle elements here would become 0. You'll be left with a lower triangular matrix, and the determinant of a lower triangular matrix is simply the product of the diagonal elements. So the determinant becomes easy to compute in this construction. What would the inverse mappings be? The inverse mappings would be x1 would be y1, of course, x2 would be G inverse of y2 and m of y1. That would be the inverse operation in this particular case. In case you'd like all data to be considered, so in the previous construction, we considered that y2 can depend on x1, but y1 cannot depend on x2. If we instead want all the elements of the output to depend on all the elements of the input, it can be done, but you may have to flip the inputs after each layer. So that way, in the next iteration, next function, remember it's a series of layers or composition of functions, you can have y1 depend on x2, and you can continue this process to ensure that all the output variables depend on all the input variables. So you can now write this as additive coupling operations also. In additive coupling operations, you can say that y1 is equal to x1 and y2 is equal to x2 plus m of x1. So in this particular case, it's not a function, but you just have y2 is equal to x2 plus m of x1. The inverse operation here would be x1 would be y1 itself, x2 would be y2 minus m of y1. In such a construction, in an additive coupling layer, in the previous case you had a g function here, but in the additive coupling layer, the Jacobian determinant will always be 1. Why do you say so? You can look at these two equations and give the answer. Because it's additive coupling, you would have dou y1 by dou x1 will be 1, dou y2 by dou x2 will also be 1, because the second term here is additive and does not depend on x2. So all those diagonal elements of your Jacobian, what are the diagonal elements of your Jacobian? In your Jacobian matrix, you would have dou y1 by dou x1, dou y2 by dou x2, so on and so forth till dou yk by, for the moment let's say dou xk, assuming both are the same dimensions. All these values, if you look at these equations, will be 1. Product of the diagonal elements will be 1. The Jacobian determinant will be 1. This is called a volume preserving operation. Remember we said the determinant, Jacobian determinant, is an estimate of how much the volume changes. For example, if you have a random variable x which has a certain density, say between 0 and 1, in this case a uniform density. If you had another random variable, say z, which goes from say 0 to 3, if its volume was like this, then you can see that the gradient would give you an answer to be 3. So for every 1 unit that you move in x, you'll move 3 units in z. So this tells you that the volume between x and the PDF of z triples, and the determinant of the gradient dou z by dou x also gives you that answer 3, which in a sense intuitively tells you how much is the volume changing in the new PDF. So when the Jacobian determinant is always 1, as in when you have an additive coupling layer, it is a volume preserving operation. So in this case, the log likelihood becomes very simple. You simply have the determinant of Jacobian term is always 1, so that term would disappear and you would have the log likelihood of px be the log likelihood of y itself. An improvement over nice was another normalizing flow method, a popular one, known as real NVP, real valued non-volume preserving normalizing flow. As the name states, it is non-volume preserving. So we definitely have to do something beyond additive coupling. What do? We have an affine coupling operation. What does the affine coupling operation do? We say y1 is equal to x1 and y2 is equal to x2 into, this is the Hadamard product, which says it's an element-wise product. So x2 is a vector and the second term here is also a vector and it's an element-wise product, into exponent of s of x1 plus t of x1. So there's a translation component and there is a scale component, which together becomes an affine transformation. The Jacobian of such a transformation would be, it would still be a lower triangular matrix because y1 does not depend on x2, x3, so on and so forth. Similarly, y2 does not depend on x3, x4 and so forth. So the Jacobian will have the upper triangular entries to be 0, and you would then have in the lower triangle entries dou y2 by dou x1, and the diagonal entry in this case would be diag of exponent of s of x1, because that's what the differentiation of dou y2 with respect to x2 will be. In this case, the Jacobian need not be 1 and hence the transformation may not be volume preserving, which perhaps is more likely in real world data. For example, if we gave z, the random variable that we considered for normalizing flow, to be a unit Gaussian, expecting that any real world data distribution will also have the same volume as that unit Gaussian may not be a very correct assumption. So in that sense, real NVP is more realistic. The inverse operation, what would it be here? x1 would be y1, equality. x2 would be y2 minus t of y1 into exponent of minus s of y1. Remember this exponential function. When you go the other side, it becomes an inverse exponential function, and that's what this term denotes. Figuratively speaking, this is how a real NVP affine coupling would look like. So you have your x1, x2, y2 depends on x1 and x2, y1 depends only on x1. How does y2 depend on x1 and x2? A translation and a scale component. The inverse, as you can see here, would look something like this, where x2 would depend on a scale component from y1 and a translation component in addition to contribution from y2. So how are all of these networks trained? So the rest of it should work like any other neural network. So it's about maximizing the likelihood. You can use standard error functions like mean square error, cross entropy to learn the networks, depending on what you're trying to reconstruct, what's the output of each of these networks, and each layer corresponds to one of these functions that you're trying to model. For example, y1 is equal to x1 would be one of the layers of the neural network. The second layer would be this, where the scale and the translation are learnt by the neural network, so on and so forth. That's how the network learns.